Okay, guys, now let's look at an application for the system of ODEs, applications, a mixing problem. So if you remember previously, we saw how to solve a mixing problem when we have, let's say, one tank. Let's say we have one tank, and then let's say we have some water or salt water coming in, and we can have some initial salt value, salt amount in the tank. And also then the water comes in, or salt water comes in, and then mixing happens, and then there's also the mixture that goes out. And then we saw that if we can call x of t, assume that x of t is the amount of salt in the tank at time t. Then we set up an ODE for x of t, and how did we set up the ODE, by the way? So the way that we set up the ODE, we said that the rate of change of x, dx to dt, is equal to rate in minus rate out. So we found the overall rate, which is rate of change of x. So that gave us a first order differential equation. And then we solved it to find x of t, as a function of time, the amount of salt at time t. So now we want to see if we have, let's say, two tanks connected together. So now suppose that we have two tanks connected together. So one tank here, one tank here, and these two are connected with some pipes, let's say. And there could be some water coming into the first tank or second tank or both of them. That depends on the problem. But anyway, so we have two tanks. And we are interested in finding the amount of salt in each tank after time t. So let's say x1 of t could be the amount of salt at time t in tank 1, and x2 of t, the amount of salt at time t in tank 2. And the goal here is to find or to set up a system of ODE, because this time we have two unknown functions with two equations. So we have a system of ODE. To set up system of ODE for x1 of t and x2 of t, and then solve it to find x1 of t and x2 of t. So let's look at an example. example, two 1,000-liter tanks. 1,000-liter tanks are with salt water. Tank 1 contains 800 liters of water with 20 grams of salt, meaning that initial amount of salt is 20 grams. With 20 grams, let me say initial 20 grams of salt. Tank 2 contains 1,000 liters of water with 80 grams of salt. Salt water with concentration concentration 1/2 gram per liter of salt enters tank 1 at the rate enters tank 1 at the rate of 4 liters per hour. Fresh water enters tank 2 at the rate 7 liters per hour. Through pipe 1, water flows from tank 2 to tank 1. Water flows from tank 2 to tank 1 at the rate of 10 liters per hour. Through pipe 2, through pipe 2, 13 liters per hour flows out of tank 1. Tank 1, and 11 liters per hour drains out of the system. I can say of which 11 liters per hour drains out of the system. And 2 liters per hour goes to tank 2. And 2 liters per hour goes to tank 2. Set up the system that will give amount of salt in each tank. set up the system of ODE. That will give the amount of salt in each tank at any given time. So let's look at the picture. We have 2 tanks that are connected together with 2 different pipes. They're called pipe number 1 and pipe number 2. So let's say this is tank 1 and this is tank 2, and connected with 2 pipes. This is pipe number 1, pipe number 2. Now, what do we know? We know that 4 liters per hour goes to tank 1, salt water, and 7 liters per hour goes to tank 2, fresh water. So 4 liters per hour goes here, 7 liters per hour goes here. Now in pipe 1, there was water going from tank 2 to tank 1 at the rate of 10 liters per hour. So tank 2 to tank 1, water goes with the rate of 10 liters per hour. From tank 1 to tank 2 in pipe 2. So it said that 13 liters per hour goes out of tank 1 through pipe 2. So 13 liters per hour goes out here. But not all of it goes to tank 2. 11 liters of it per hour goes here out of the system. And only 2 liters per hour goes to tank 2. So these are the water or water salt going into each of the tanks. So in tank 1 and tank 2, each of them, there are some water or salt water coming in, and through pipe 1, we have from tank 2 to tank 1, and from pipe 2 through pipe 2, we have from tank 1 to tank 2. Now, we want to set up the ODE for each xi. So dx1 to dt is going to be rate in minus rate out for tank 1. For tank 1, now rate in, what is the rate in? So we have 4 liters per hour coming into tank 1. So 4 liters per hour. But remember the unit for dx to dt, so x is the amount of salt. So the unit should be gram per hour. Now this is 4 liters per hour, so I have to multiply it with gram per liter, so that I get gram per hour for the rate in. And this was given in the question. It was saying 1/2 gram per liter. The 4 liter that comes in into tank 1 has the concentration of 1/2 gram per liter. So I have to multiply this number by 1/2 gram per liter minus rate out. Now, what is the rate out? So we have some water. So some water going into tank 1, some water going out to going out from tank 1. Now 10 liter goes to tank 1, 13 liter goes out. And originally we have 800 liter in tank 1. So after each hour, how much is added to tank 1? How much water is added to tank 1? Originally is 800 liter. You see? Let's write it here. Originally, tank 1 contains 800 liter, and after each hour, now let's see what happens after each hour. 4 liter comes in here. 4 liter comes in here. 10 liter comes in here, so that's 14 liter coming in. 13 liter goes out. So overall, in each hour, 1 liter is added to tank 1. So after each hour, 1 liter is added. So I can say after time t, tank 1 contains how many liter? If after 1 hour, 1 liter is added, like after 2 hours, 2 liters will be added. After 3 hours, 3 liters will be added. After 1/2 hour, 1/2 liter will be added, and so on. So after t hours, after time t or after t hours, t liters will be added. After time t, or I can say after t hours, t liters will be added. So I can say V of t is equal to, or V1 of t is equal to 800 plus t. So that's amount of or 800 plus t, basically liter is contained in tank 1. After t hours, tank 1 contains 800 plus t liters. Originally, it contains 800 liters, but after 1 hour, 1 liter will be added, and after t hours, t liters will be added. So overall, 800 plus t liters is contained in tank 1 after t hours. Now we can do a similar calculation for tank 2. So again, originally in tank 2, tank 2 contains 1000 liter. And again, after each hour, how much will be added to tank 2? So let's see. After each hour, 7 liters added here. 2 liter added here, so that's 6 liters, 9 liters, that's 9 liters, and 10 liter goes out. So overall 9 liter goes in, comes in, 10 liter goes out after each hour. So overall 9 liter comes in, 10 liter goes out, means 1 liter overall goes out after each hour. So after each hour, 1 liter goes out of tank 2. So after time t, or after t hours, so after 1 hour, 1 liter will be deducted. After 2 hours, 2 liters will be deducted. After 1/2 hour, 1/2 liter will be deducted, and so on. So after t hours, t liter will be deducted from tank 2. So that means V2 of t is equal to 1000 minus t liter is contained in tank 2 after t hours. All right, now let's go back to our ODE that we were trying to set up. Now we said dx1 to dt is rate in minus rate out. So this one is rate in. Now we have rate out. Let's look at the system. We have rate out. So 13 liter per hour goes out from tank 1. So minus 13 liter per hour times, as we said for the first term, this liter per hour must be multiplied with some number with the unit of gram per liter, so that we have gram per hour overall. Now this has to be multiplied with what number? So what is the in tank? So this 13 was in tank 1. And it was going out of system from out of tank 1. So how many gram per liter? So how many gram do we have? How many gram of salt do we have in tank 1 after time t? Well, that's exactly x1 of t. That's the quantity that we want to find it, right? So x1 of t is the amount of salt at tank 1 after time t. This is how we define x1 of t. Remember, x1 of t, the amount of salt at time t in tank 1. So we want to know that this number must be multiplied with which number? It has to be multiplied with the amount of salt in tank 1, which is in gram, per the amount of salt water that we have in tank 1 in liter. How many liter do we have in tank 1 after time t? So that's, we already calculated it. It was 800 plus t. So this should be minus 13 liter per hour times x1 of t divided by V1, which is 800 plus t. Gram per liter. So again, 13 liter per hour goes out of tank 1, that is given in the question. But what is the concentration of that water that goes out, because I need to know the concentration, which will be in gram per liter. I should multiply with this number so that I get the unit that this quantity is supposed to have, which is gram per hour. What is the concentration of the water that goes out? In order to find the concentration of this water in tank 1, what do I need to know? I need to know the amount of salt at time t in tank 1, which is denoted by x1 of t. And the amount of salt water in liter in tank 1 after t hours, which is what we calculated here. It was 800 plus t. So the concentration, so the amount of salt water we calculated here, 800 plus t, and the amount of salt is x1 of t. So the concentration will be x1 of t divided by 800 plus t. So this part is a little bit confusing for some students when I ask what is the amount of salt in tank 1 at time t. Sometimes they give some numbers or some expressions, but you have to think about that. You know, the amount of salt in tank 1 at time t is exactly what you want to find. You haven't found it yet. But that's what we denoted by x1 of t. x1 of t is the amount of salt in tank 1 at time t is what we want to find. So we can keep it as x1 of t, and then we have 800 plus t liter in tank 1. So the concentration will be x1 of t divided by 800 plus t. So this part, the salt water goes out of tank 1, but so see, we included this part where salt water comes in. We included this part where the salt water goes out, but there's also one more part through pipe 1 where the salt water goes in. Because it goes in, it will have plus sign. Remember, whatever goes in has plus sign, whatever goes out has minus sign. Here we have two types of water coming in, and one type of water going out. So two terms with positive terms, a positive sign, and one term with negative sign. We already included this part. Now this part has positive sign, and one more term with positive sign. So plus. Now this one, 10 liter per hour is the amount of salt water per hour. 10 liter that goes in tank 1 is 10 liter per hour. So plus 10 liter per hour. And then I have to multiply with the concentration of this salt water. What is the concentration of this salt water? Well, what is the amount of salt in tank 2 at time t? So if you remember, we had a similar situation for tank 1. So the amount of salt at time t in tank 2 is exactly the quantity that we want to find it. And we denoted it by x2 of t. So x2 of t is the amount of salt at time t in tank 2. And how many liter do we have in tank 2 at time t? Again, we already calculated this here. We denoted with V2 of t. That's amount of salt water we have after time t. So 1000 minus t liter will be contained in tank 2 after time t. So in order to find the concentration, I just need to simply divide these two numbers, the amount of salt in gram and the amount of salt water in liter. If I divide these two numbers, so x2 of t divided by 1000 minus t, gram per liter. So this is the ODE for the amount of salt in tank 1. So dx1 to dt, dx1 to dt, 4 times 1/2, so that's 2. So 2 minus 13x1 divided by 800 plus t. 13x1 divided by 800 plus t. And then plus 10 times x2 divided by 1000, 1000 minus t. So this is the ODE for the amount of salt in tank 1. Similarly, we can set up the ODE for the amount of salt in tank 2. So similarly, for tank 2, what can we say? We can say that dx2 to dt is equal to rate in minus rate out So again, let's see what type of water or salt water do we have going in, coming in and going out of tank 2. Well, we have 7 liters per hour coming in. And what is the concentration of this 7 liters per hour? It says in the question that the concentration is 0 basically, because fresh water comes into tank 2 with this rate. So if it's fresh water, that means there's no salt and the concentration is 0 gram per liter basically. So I can say 7 liters per hour times the concentration, which is 0 gram per liter. And then we have this 10 liters per hour that goes out. So it will be included with a minus sign. So minus 10 liters per hour. I have to multiply this now with the concentration of this water. This water, we already calculated the concentration, is the water that goes out from tank 2. So it's the concentration of the water, salt water in tank 2. Because this water goes out from tank 2, so the concentration of it is the concentration of the salt water in tank 2. And we already calculated that. We saw that x2 of t is the amount of gram in tank 2, amount of salt in gram in tank 2 at time t. And V2 of t is the amount of salt water in liter, which was, if you remember, 1000 minus t. So I have to multiply this with x2 of t divided by 1000 minus t. The unit will be gram per liter. Plus, so see, this water comes in, I included with positive sign. This water goes out, I included with negative sign. This water goes in again, comes in. So again, I need to include it with the positive sign. How much? 2 liters per hour. 2 liters per hour, so plus 2 liters per hour. And then I have to multiply this with the concentration. Concentration of what? Because this water is coming into tank 1 from tank, coming into tank 2 from tank 1. So originally this water comes from tank 1. So concentration of this water is same as concentration of tank 1. How much is the concentration of salt water in tank 1? Again, we already calculated this quantity. In order to find the concentration, I need to know amount of salt in gram in tank 1, which is denoted by x1 of t. And in tank 1, we have V1 of t liter, which we calculated as 800 plus t liter. of salt water at time t. So I need to again divide these two numbers. So times x1 of t divided by 800 plus t gram per liter. So we can say that dx2 to dt is equal to, so 7 times 0, that's 0. So minus 10x2 divided by 1000 minus t. And then plus 2x1 divided by 800. 2x1 divided by 800 plus t. So our system of ODE will be as follows. System of ODE. So we have dx1 to dt equals 2 minus, so this quantity 2 minus 13x1 divided by 800 plus t plus 10x2 divided by 1000 minus t and then dx2 to dt was equal to minus 10x2 divided by 1000 minus t plus 2x1 divided by 800 plus t. So these are the two ODEs with two unknown functions, x1 of t and x2 of t, which were denoting the amount of salt at time t in tank 1 and tank 2 respectively. And what are the initial conditions? So with the initial conditions, the initial amount of salt in tank 1 and tank 2 were given in the question, x1 of 0 and x2 of 0. x1 of 0 means initial amount of salt in tank 1. x2 of 0 means initial amount of salt in tank 2. In tank 1, if you remember, we had initially 20 grams of salt in tank 1. And in tank 2, we had initially 80 grams of salt. So x1 of 0 is equal to 20 and x2 of 0 is equal to 80. So this is what the question was asking from us. Now let's add part B to this question, part B. Write the system above in the matrix form. So if you want to write in the matrix form, we can define a vector x, which consists of two entries, x1 and x2 are unknown functions as usual. So x1, x is equal to, let's define it as x1 of t and x2 of t. So this will be basically x of t because each entry is a function of t. So this will be also a function of t. Now x prime can be written as, so minus 13. So this is a constant term. 2 is a constant term which I can include it later. So let's forget about this term for now. So these are the coefficients basically, minus 13 over 800 plus t and 10 over 1000 minus t. These are the coefficients which I can include them in my matrix. So minus 13 divided by 800 plus t, and 10 over 1000 minus t, and here minus 10 over 1000 minus t, and then 2 over 800 plus t, times x1 of t, x2 of t. I can also, just for consistency, I can write the left-hand side as x1 of t prime and x2 of t prime for now, and then later I can replace it with the vector x. So if you multiply this matrix with this vector, you know that the matrix vector multiplication is row by column. So if you multiply this row by this column, then you get this expression here, apart from this term, which I still need to include it later. And similarly, if you multiply this row by this column, then you get this expression, which is supposed to be equal to x dx2 to dt, or x2 prime. But then I just need to include this additional term here, which I can include it as a vector. Remember, our system of ODEs could be written in the form x prime equals ax in the homogeneous case. And in the non-homogeneous case, we could write it as x prime equals ax plus g of t for some vector g of t. So this can be included in that part g of t. So I can say this is x prime equals ax plus 2 and 0. So this is basically my a, and this is my g of t. So x prime equals ax plus g of t with initial condition, or before writing the initial condition, I can write this as x prime equals a x plus g of t with x equals x1 of t, x2 of t, and a and g of t as defined above. G of t as defined above. And what is the initial condition? I can also write the initial condition in the vector form with the initial condition x of 0 equals, so initial conditions are these two, x1 of 0, 20, x2 of 0, 80. And I know that x1 and x2 can be written as one vector x. So instead of x1 of 0, x2, 20, x2 of 0, 80, I can say x of 0 as a vector will be equal to the vector 20 and 80. So 20 here, 20 and 80. Now this is for part B. We wrote it in the matrix form. Now let me add another part to this question, part C. Part C, adjust numbers. Adjust the numbers given in the question so that the matrix A found in part B becomes a matrix with constant coefficients or with constant entries and solve the resulting system. So here, see, we could write x prime as ax plus g of t, but there is an issue here. We already saw how to solve x prime equals ax plus g of t in the case where entries of A are constants. Remember, we discussed about eigenvalues of A, whether they're positive or real or distinct or complex or distinct and real, distinct and complex, or repeated eigenvalue. But in all of those cases, the entries were constants, they were numbers. They were not functions of t. This part g of t was allowed to be a function. We could have, for example, 2t instead of 2 and 0, we could have 2t and 0. We covered that because we could use variation parameters or undetermined coefficients to find the particular solution. But for finding a complementary solution or XC, we only consider the cases where the entries of A were constants, not entries with functions of t. So we want to see whether we can adjust the numbers given the question. So the numbers, I mean like these numbers, like 4 liter per hour, 7 liter per hour here, 10 here, 13 here, 11 here, 2 here. So can I adjust one or few of these numbers, like 4, 7, 10, 13, change these numbers a little so that I have a system with the matrix that has constant entries. And in that case, well, I will be able to solve the system with the methods that we already learned. So can I change one or few of these numbers so that this matrix A here, becomes a matrix with constant entries instead of entries that are functions of t. Okay, before providing the answer for this part, I think I made a mistake in writing my matrix here because this is minus 10x2 over 1000 minus t, and this is plus 2x1 over 800 plus t. So the second row of the matrix, the first entry will be 2 over 800 plus t because that's the coefficient of x1. And second entry will be minus 10 over 1000 minus t, which is the coefficient of x2. So I need to just replace these two numbers, 2 over 800 plus t and minus 10 over 1000 minus t. Now this part, part C, where we want to adjust the numbers so that the entries will not will become constants. So where is the dependency on t? If you look at the entries of the matrix, where does the dependency come from? The dependency, as you can see, are in these denominators. And these denominators, where if you remember, what were these denominators? They were the volumes of water or salt water in tank 1 and tank 2. What we called it V1 of t and V2 of t. 800 plus t appears here and here. 1000 minus t appears here and here. So if you remember, so V1 of t, 800 plus t, V2 of t, 1000 minus t. So if we can adjust the numbers so that this V1 of t and V2 of t become constants rather than functions of t, then we will have a matrix with constant coefficients or constant entries. So we need to see how we can adjust the numbers so that V1 of t and V2 of t do not change over time. They remain constants. So for example, V1 of t originally there were 800 liter, and in our case, we saw that 1 liter will be added after each hour. So we don't want this. We want 800 liter remain 800 liter after 1 hour, 800 liter after 2 hours, 800 liter after time t remain 800 liter. So how can I achieve that? So if you look at tank 1, there are 4 liter coming in here, 10 liter coming in here, so that's 14 liter coming in. So if 14 liter goes out, then overall 0 liter comes in and goes out, and 800 liter remains 800 liter. Similarly, in tank 2, 10 liter goes out, so 7 liter comes in. So if instead of 2 here, I had 3 coming in, then 7 plus 3 comes in, that's 10, 10 comes in, 10 goes out, overall 0. So I need to add 1 unit to this, which will add 1 unit to this as well. So 14 is the number that we came up with it before as well. If 14 goes out, 14 goes out here, this 11, we can keep it as 11. 14 goes out here, cancels out everything for tank 1. 14 goes out, 4 comes in, 10 comes in, so 14 comes in, 14 goes out, everything cancels out. And also for this additional 1 liter here, we can add it to this 2. This 2 becomes 3. So then 3 and 7, 10 comes in, and 10 goes out. Again, overall, that will be 0. So we just need to add 1 unit to this, and 1 unit to this. And then V1 of t, V2 of t become constant over time. They won't change as t changes. And then we will have matrix with constant entries. So, so I can say that since the dependency on t comes from dependency on t in the expressions derived for V1 of t and V2 of t above, in order to eliminate this dependency on t, we need to choose or adjust the numbers so that, or such that, V1 of t and V2 of t become constants. So how can I achieve that? So for tank 1, 4 plus 10 liter, which is equal to 14 liter, comes in. So if we replace 13 liter with 14 liter going out of tank 1, then V1 of t will not change over time. Because everything will cancel out, the amount that comes in and the amount that goes out will cancel out. Seems that my screen is freezed. So we were saying that 14 liter 4 plus 10, 14 liter coming in. So if instead of this 13 liter that goes out, instead of this 13 liter that goes out, we have 14 liters that goes out. Then 14 liter coming in, 14 liter going out. And after 1 hour or after 2 hours or after t hours, the amount of salt water remains 800 liters. The liters will become constant, unchanged. And we will have V1 of t equals 800. Similarly, in tank 2, we have 10 liter going out. 10 liter going out. So if instead of this 2 liter, we had 3 liter, then 3 liter coming in, 7 liter coming in, that's 10 liter going out, they cancel out, and V2 of t remains constant as well. So in tank 2, we have 10 liter per hour going out. So if instead of 2 liter per hour, we had 3 liter per hour coming in, then overall 7 plus 3 equals 10 liter per hour comes in, and overall V2 of t remains constant. V2 of t will be 1000 liters. So this will be the new picture. Again, tank 1 here, tank 2 here. Again, 2 pipes, 10 liter. And going out of tank 2, 4 liter here, and 7 liter here. And so this one, 14 this time. Goes out of tank 1. Again, 11 liter goes out of the system. And 3 liter goes to tank 2. And again, as we said, 4 plus 10, 14 comes in, 14 goes out for tank 2. And for tank 1 and for tank 2, 7 plus 3, 10 comes in, 10 goes out for tank 2. So with the new numbers, the system will be with these new numbers. The system will be x prime equals ax plus g of t with x of 0 is still same as before. What was x of 0? X of 0 was 20 and 80. And the matrix A. So how will matrix A change? So matrix A, these numbers that we had, 800 plus the 1000 minus C, there will be V1 of t, V2 of t. And now we have adjusted the numbers so that this V1 of t is always 800, V2 of t is always 1000. Everything else is still same as before. So I just need to change these numbers to 800, this one to 1000, this one to 800, this one to 1000. So then I'll have minus 13 over 800. And the other one was 10 over 1000. Minus 2 over 800. I think it was 2 over 800 and minus 10 over 1000. 2 over 800 minus 10 over 1000. And g of t is still same as before, 2 and 0. So just by adjusting two of the numbers, so this 13, we change it to 14. And once we change this, we have to change one of these two numbers. And we kept this one the same, and we changed this one from 2 to 3. Only by this simple change, now we have a system of the form x prime equals ax plus g of t. And A now is a matrix with constant entries, which means we are now able to solve this system because we already learned how to solve this system. We know that we can write the solution as x equals xc plus xp. X is the solution for x prime equals ax. How do we find it? How do we find xc? We just need to find eigenvalues, eigenvectors of this. If there are two different eigenvalues, then two different eigenvectors c1, c2, c1 e to power lambda 1t and c2 e to power lambda 2t, and some linear combination of it. And if there is a repeated eigenvalue, again, we saw how to deal with it. And xp, how do we find xp? Again, you can use undetermined coefficients or variational parameters to find xp. And here the initial condition is also given. So once you write it as xc plus xp, there will be some constants involved, two constants involved. So you can find those two constants by writing the initial condition. So we can first write the general solution, and then the general solution will include two constants like alpha 1 and alpha 2. And you can find those constants by using the initial condition. We know that x of 0 is 20 and 80. So let me leave the rest as exercise. Find the solution of the system above. I can also include the hint that the solution x can be written as xc plus xp. So find xc, find the eigenvalues eigenvectors of A. To find xp, the easiest way to find xp is to use undetermined coefficients method. Undetermined coefficients method, and then x equals xc plus xp. Lastly, find two constants which are included in xc by using the initial condition that we had here, the initial condition x of 0 equals 20 and 80. If you write the initial condition, then you will see that you have two equations with two unknowns, let's say alpha 1 and alpha 2, your constants that are included in xc. You can solve that system, find alpha 1, alpha 2, and once you do that, then you will have the unique solution which was written in this form, and there were two constants involved in xc, and you already found them with the initial conditions, and then you have the final answer. Okay, guys, so we saw how to solve the system of ODE here. Finding the particular solution, we use the variation of parameters. Last time we saw how to find xp using undetermined coefficient. This time we saw how to find xp using variation of parameters. And we already also know how to solve the homogeneous system, x prime equals ax. And then we also looked at some application for like mixing problems. We already saw if you had one tank, how to solve mixing problems. We saw it in the previous chapters by setting up a first order ODE. This time we had two tanks connected together. So we had two unknown functions with two equations. And then we set up the ODE, and we saw that if we have a matrix with constant entries, then we can solve it and find a unique solution once we have the initial condition. Okay, guys, so that's all for today. Thank you and see you next time.